Hey, I'm Arjun, and today I'll teach you a little bit about duality of matter, or simply wave-particle duality. Let's start with defining some useful terms. Electromagnetic radiation is the radiation or emission of waves that don't need a medium like air to travel. A good example is light. Speed of waves. Almost all of us know how to calculate this. If a wave can travel a distance lambda in t seconds at a speed v, we get v equals lambda by t. Now we know that frequency is 1 upon time, so velocity is wavelength into frequency. For example, this will be the speed of light. Black body radiation. First, a black body is an ideal body that absorbs all electromagnetic radiation that falls on it. A black body also emits a light called black body radiation, which is completely dependent on the temperature of the body and nothing else like shape or composition. Due to this radiation, the bodies usually glow brightly at high temperatures and light at low temperatures. This graph accurately represents the radiation pattern. The one with the lowest heat has the lowest intensity and also the maximum peak frequency. Noticing a pattern, Wilhelm Wien made a law stating that the product of the maximum wavelength for the emission into the temperature always equals a constant, B, or Wien's displacement constant. But it was Max Planck who formulated the full equation for blackbody radiation. His equation related the intensity of radiation produced at a temperature to either wavelength or frequency. This equation introduced the concept of quantum. The h, or the Planck's constant, times nu, the frequency, represent the energy associated with a photon at different frequencies, or energy equals h into nu. Photoelectric effect. Now this is where it gets really interesting. The photoelectric effect is a phenomenon which showed that when light hits an electron on a metal surface, the electron is emitted from the metal. This was termed as a photoelectron. At the time, it was believed that light only had a wave nature, so by theory, if a low-intensity light hit a metal, the light would transfer energy to the electron. When the kinetic energy was high enough, the electron would escape. But this was not the case. In 1905, Albert Einstein published a paper emphasizing that light energy also had a particle form and the energy was carried in packets. This was experimentally proved later on. His discovery was labeled the law of photoelectric effect and the discrete packets were called photons. With the works of various great minds, Louis de Broglie finally put together and proposed the idea that not only photons show both wave and particle characteristics but also material particles such as electrons and all matter do. His equation was simply this: wavelength of an object equals the Planck constant upon the momentum of the object. With this equation, the wavelength of any moving object could be calculated, and for bigger masses, the value was so small it was negligible. This showed why the wave characteristic of bigger particles were not identified due to a negligible wavelength. Here is how he came to this conclusion. We know that E equals to h nu and mc square, thus h nu equals to mc square. We know the speed of light, which can be equated according to its frequency, and putting this in the first equation, we get lambda equals h upon mc. Now replacing the speed of light by the speed of any object, we get lambda equals h by mv. Now we know momentum is mass into velocity, thus the wavelength of any object is the Planck constant upon its momentum.